Okay, so today we're going to do a series of labs so students can have hands-on experience with different forces and loads and shapes that can affect their designs when they are building their structures. So these are kind of the basics of structural engineering. The first lab is going to be a forces lab, and we really want them to practice using the proper scientific words for these forces, and for them to be able to handle things and kind of see the forces in action. So we kind of have our go-to materials that we often use during these activities. We also have a little grid where the groups will be taking notes and documenting their observations of what's going on with their materials. And it's really simple. It's going to be a little repetitive because they're going to do the same forces or apply the same forces to each of the materials, but it'll be fun. So the first one is going to be the jumbo marshmallow. I'll take one of these, and you'll explain to the students that compression is a squeezing force. So when you imagine a building, if you look at the first story, that's being compressed or squeezed by all of the stories on top of it. So what do they think is going to happen to this jumbo marshmallow when we compress it or squeeze it? Remember, they should always practice making predictions and giving a reason for their prediction. And then once they actually apply the force, they can make observations and record them. So what's their prediction? What's going to happen to this jumbo marshmallow when we compress it or apply the compression force? Okay, so today we're going to do a series of labs so students can have hands-on experience with different forces and loads and shapes that can affect their designs when they are building their structures. So these are kind of the basics of structural engineering. The first lab is going to be a forces lab, and we really want them to practice using the proper scientific words for these forces, and for them to be able to handle things and kind of see the forces in action. So we kind of have our go-to materials that we often use during these activities. We also have a little grid where the groups will be taking notes and documenting their observations of what's going on with their materials. And it's really simple. It's going to be a little repetitive because they're going to do the same forces or apply the same forces to each of the materials, but it'll be fun. So the first one is going to be the jumbo marshmallow. I'll take one of these, and you'll explain to the students that compression is a squeezing force. So when you imagine a building, if you look at the first story, that's being compressed or squeezed by all of the stories on top of it. So what do they think is going to happen to this jumbo marshmallow when we compress it or squeeze it? Remember, they should always practice making predictions and giving a reason for their prediction. And then once they actually apply the force, they can make observations and record them. So what's their prediction? What's going to happen to this jumbo marshmallow when we compress it or apply the compression force? I'm going to predict that it's going to shrink in size. It's going to be squished or smashed a little bit. And the reason for my prediction is because I know from my experience that marshmallows are fairly soft. They're not really strong or sturdy materials. So let's go ahead and do it. We will compress it or apply that compression force. Okay, my prediction was correct. It did get squeezed or smushed. And so if they're using the word compress and compression, that's great. If they use the word squeeze to describe it, that's totally fine, as long as they're using both. Okay, so compression is a squeezing force. Doesn't matter if I do it this way, same thing happens. So they could draw a little picture of that on their grid. Okay, squeezes, decreases in size by about a half, and then I could draw a little simple picture. This is before compression, And then this is with compression. There's my fingers pressing it down. Okay, they kind of squish out at the side. So the material gets a little wider and shorter as it's being compressed. Put that aside. I actually think that it's going to hold up to tension forces pretty well. So let's stretch. It's breaking, so it's deforming very easily. And it's going to pull apart. Okay, so it actually, I mean, it held up to the tension forces for a little bit, but then it kind of just broke in half, so, or tore in half. Okay, does not hold up very well. And I'll draw the marshmallow. They don't have to be artists. Okay, so that's tension. They could finish it with the rest of the materials. And then we're gonna do bending, which doesn't really need another word for it. It's just bending. So here's our graham cracker. We can remember that the graham cracker held up very well, surprisingly, to compression forces when we squeezed it. So what's gonna happen when we bend it? So my prediction is it's not going to hold up to bending forces really well, kind of for the same reason that I predicted with the compression forces, even though I was wrong with that one. I think that you could easily break a graham cracker. They seem pretty brittle. They're not very flexible. They're not very rigid. So when you bend it, I think it's just going to crack in half. So that's my prediction. I gave my evidence or my reason for it, and let's make our observation. So I was right, it easily cracks in half. So it's really strange, right? It holds up to compression forces really well, but it bends very easily. So different materials can have very different responses to different forces. Next load we're going to do is the load slab. Forces that act on structures are called loads, and you could think of them as the weight that structures must withstand and withhold. There are lots of different types of loads. We're just going to go over two simple ones with our students. The first type of load is called a dead load, and that's just the weight of the structure itself. So all of the materials that are permanently attached to the structure, like columns and beams and tiles and nuts and bolts, that's the dead load. So if I were to build a very simple structure here of 2 marshmallows and a graham cracker, my dead load would be those 2 marshmallows and that graham cracker. And that seems simple enough, but you also have to make sure that through the design of your structure, the structure itself can actually withhold its own dead load. Because what would happen if I decided to change my design and I wanted a nice little L shape and I got rid of this marshmallow? Would my structure, would my design be able to withhold its own dead load? Probably not, is my guess, my prediction. So I'm just gonna let go of my finger, and yeah. Okay, so while it seems simple enough, you have to make sure that your design takes into consideration the weight of the materials themselves, not just any external weights that we put on top of it. So I'm gonna keep my nice simple structure right there. The next kind of load we're gonna talk about is the live load. The live load is the weight of all of the things that can move around or in or on a structure that might change day to day. People that walk into a building, all the furniture that's moved around in a building, if it's a bridge, the cars that go across the bridge. And so these are live loads, things that may not stay the same, that change day to day. And so let's think of this marshmallow. If I kind of just apply kind of like a live load to just something, a weight, a top-down weight, what do you think is going to happen? I think that the marshmallows are going to be pressed down a little bit. They're going to be compressed, and they'll be fine, but I think that my graham cracker is going to break in half because it bends easily. We know that. So I'm just going to press down with my finger, not too hard, just gently, and we'll see what happens when I apply this live load. Okay, so it cracks, and you could start incorporating the idea of reinforcing or strengthening a structure. So how can I make sure that my marshmallow bridge is going to withstand some external live loads? One way to do that is to make this part of your bridge thicker. So what's my prediction? Will 2 graham crackers be able to withstand external forces, kind of this other live load that might change? And it does. So I'm actually applying the same kind of force, but it's not breaking. So one way to strengthen a structure when it's being affected by external loads, some that may change day to day, is just to make it stronger or thicker. So it survived. Okay, and why do we think so? One, the marshmallows are being compressed a little bit, so they're kind of absorbing the energy of this external force, this kind of random live load of my finger kind of pressing down at different spots. And it's staying in one piece. Okay, so that's an interesting thing to observe. The next lab we're going to do is the Strong Shapes lab. You're going to ask students to make a prediction. Which do they think is the stronger shape? A triangle or a square? And whatever they predict, they have to give a reason for it, so give them time to do that. And then you're going to have them go ahead and build a 3D cube and a 3D pyramid. And without even applying any stress or force, except for gravity, to the cube or the triangle, let's just make an observation. So I'm going to let go. And just by looking at the cube versus the triangle, now what do they think is the stronger shape? A triangle or a square? And what's their reason? What observations are they using to make their claim? I would say clearly a triangle is the stronger shape, because we're not even touching the cube made up of squares at this point, and it already deformed or lost its shape. And that's definitely not something you would want in a building. Okay, so let's try to stand it up again. And we'll apply a few of the forces that we learned about in the first lab. So compression, let's squeeze it. Let's apply some torsion forces. Let's see if it will twist. Okay, so I think without a doubt, we have proven with our empirical observations that triangles are stronger shapes than squares. So the question is, why don't we just all live in pyramids as buildings? Why are most of our buildings rectangular? And that's a good question. You could have the students discuss why. One answer might be that there's not a lot of usable space. You kind of lose the space up here at the top of a pyramid. Also, in terms of holding loads, it's really hard to balance loads on top of a pyramid. You also can't really build them that high. So they just don't seem, even though they're stronger, they don't seem as practical in terms of a building shape. So if you're going to be using mostly rectangles and squares, how can you make rectangles and squares stronger? And one way to do that is to add triangles to your squares. And here's a perfect way to teach the students about reinforcing their structures. Okay, so if we know that triangles are the strongest shapes, how can we add triangles to our squares? One way is through cross bracing. And when you do cross bracing, what you're doing is literally adding cross shapes into your squares. So So it seems pretty good. I'll show you one more way to use triangles within your square shapes. So let's flip it over so we have this free space right here. We can add something called a truss. And a truss is literally adding, if you could see it, a triangle within the square. I just lost a piece right there. So just like that. Can you see how this piece right here? Can you see that triangle right there? Okay, so again, here's my truss. Here's that triangle shape within that square. So now all 6 sides have been reinforced with triangle shapes. Now let's test the strength of our square, our cube. It is exponentially stronger at this point based off of our original cube that just fell over every single moment if we were holding on to it. This one seems pretty stable and it is withholding many of the stresses or many of the forces that we're applying to it. Okay, so again we have the cross bracing, just putting that cross shape within the square, and then we have the trusses, which is putting the triangle shape within the square. There's one more way that you can reinforce a structure, and that's called a buttress. And I will show you how to do that. Okay. So those are 3 different ways that you can add triangle shapes to your squares and therefore reinforce your structure.